Ever driven on a brand new road? Feeling that smooth, satisfying glide, and wondered about the incredible engineering happening just beneath your tires. Or maybe how long it's really designed to last before you start seeing those first cracks appear. Well, today we're taking a deep dive into the hidden world of road construction. We're looking at the materials that keep our journeys smooth, focusing on some fascinating new research that might just change how we build our roads. Our mission today is to unpack a really compelling recent study. It's titled Fatigue Performance of Flexible Pavements with Cement-Bound Granular Material, CBGM, by Budziszewski, Major, and Leonarel, just published this year. And look, this isn't just about concrete mixes. It's really about the very foundation of our infrastructure and, well, the surprising differences in how we predict its durability. You see, the models engineers use, they can give wildly different answers about road life. That has massive implications. You probably don't think much about the layers beneath the asphalt. I mean, why would you? But understanding them is actually crucial for road longevity, for cost effectiveness, and yeah, even for safety. We're talking about making sure our roads don't crack prematurely, that they don't develop those annoying ruts, and that they can handle the incredible weight of traffic day in and day out, ideally for decades.
And what's truly fascinating here, I think, is that we're looking at a critical, often unseen component of these road structures, this cement-bound granular material, CBGM, as you said, and analyzing how it performs under one of the biggest stresses it faces right at the start, construction traffic. This study really throws a spotlight on how our, sophisticated design models actually predict real-world performance, especially when different criteria, different ways of measuring lead to vastly different conclusions about a road's immediate resilience and its long-term lifespan. It's almost like two different fortune tellers giving completely opposite predictions for the same road. It's quite something.
Okay, let's unpack this then. Many roads, especially in places like Poland, where this research comes from, are what we call flexible pavements. Think of them maybe like layered cakes. You've got asphalt on top of a granular base. But beneath that, there's often this key player, CBGM, which is essentially what gravel and sand mixed with a bit of cement.
Precisely. Yeah, granular material like gravel, sand, mixed with a small amount of cement. It forms this semi-rigid, incredibly strong layer. It serves as a crucial subbase layer. Now, to design these structures, engineers use what's called a mechanistic empirical approach.
Okay, mechanistic empirical. Sounds complex.
It is, but in simple terms, they don't just guess. They create a structural model. You could think of it like a digital twin of the road. This helps them understand the physics, how the road behaves under load. The mechanistic part, that's applying principles of mechanics to calculate stresses and strains. And the empirical part means they fine-tune these models using real-world observations, field tests.
Right, so they treat each layer of the pavement as sort of an elastic body, meaning it deforms under load but bounces back, at least initially. And they assign specific properties, thickness, stiffness, that's the elastic modulus you mentioned, how resistant it is, and Poisson's ratio, which is about how it squashes versus stretches.
Okay.
And all that lets them estimate the stresses and strains each layer feels when, say, a heavy truck drives over.
Yeah.
And this estimation is key for what you call fatigue life assessment, right? Predicting how long it lasts.
Absolutely. Fatigue life is, well, putting it simply, it's the number of equivalent single-axle loads, or easels, a pavement can withstand before it reaches a defined failure condition.
Easels, like a standard unit of truck impact.
Sort of, yeah. Think of an easel as a standardized unit of traffic load. So whether it's a small car or a huge truck, engineers can convert its impact into how much wear and tear it puts on the road. It allows for a universal measure. Now, for flexible pavements, we primarily look at two main failure criteria. First, the cracking of the asphalt layer. That happens because of tensile strains at the bottom, the pulling apart motion when a wheel passes over. And second, the formation of permanent ruts or deformations. That's linked to vertical compressive strain down at the subgrade level, so the pushing down, the compacting effect into the earth beneath the road structure. However, for these cement-bound layers like CBGM, there's also another risk, vertical crushing. And what's particularly interesting about CBGM, really key here, is that its mechanical behavior isn't constant. It actually changes over time. It typically goes through two main working phases, almost like a life cycle. First, there's an uncracked phase. Here it behaves like a rigid, very strong plate, distributing loads really effectively. But then it enters a cracked phase, And this phase itself progresses. It starts with large blocks forming. Then it fragments into smaller blocks. And eventually, the material can end up acting more like an unbound granular layer. It loses a lot of its initial stiffness. This progressive fragmentation significantly affects its stiffness and its other mechanical properties. Basically, it gets weaker and less able to carry heavy loads effectively.
Okay, here's where it gets really interesting and maybe a little bit mysterious. You mentioned stiffness modulus, how resistant it is. That sounds critical. The study mentions Judice's work, showing how this modulus changes dramatically depending on the CBGM strength, the type of aggregate, and crucially, whether it's in that strong, uncracked state or the weaker cracked state. Like the example you gave, it could start off almost like steel, stiffness-wise.
That's right, incredibly high, maybe 4.5 gigapascals or GPa.
But then, in a small block cracked state, it could plummet to something more like dense rubber, like 160 to 350 megapascals in PA.
Exactly. That's a huge difference in stiffness, orders of magnitude, potentially.
Wow, and that huge difference brings us to the core of this mystery you mentioned.
It does, because the 2014 Polish catalog for pavement design, which is a key design guide used there, it made a really noteworthy assumption for these CBGM subbase layers. It entirely omitted the uncracked phase from consideration in its main design tables.
It just ignored the strongest phase.
Essentially, yes, for the standard calculations. For stronger CBGM mixtures, it just assumed a cracked state with small blocks already formed, which significantly reduces the assumed stiffness right from the get-go. And for the C1.52 mixture, which is very common, it specifically assumed a stiffness modulus of E200 MPa.
200 MPa, that's what, roughly half of what they assume for just plain crushed aggregate, even though the CBGM starts off much, much stronger.
Precisely, even though it starts off potentially much, much stiffer than regular unbound aggregate.
Okay, if the CBGM layer starts off super strong, like steel, but the official design guide treats it like it's already significantly cracked and weaker, like dense rubber, what does that actually mean for the roads you drive on? Are we over-designing them? Are we spending money on materials we don't necessarily need based on this assumption?
You've absolutely hit on the crucial point there. This assumption of lower stiffness, basically, assuming the CBGM layer is already significantly cracked before it even sees much traffic, it leads to designs with what the paper calls considerable reserves in fatigue life. In simpler terms, yeah, the road might be over-designed, stronger, and probably more expensive than it strictly needs to be according to these specific calculations.
It's like building a bridge to withstand a Cat 5 hurricane when historical data only shows strong breezes in the area.
That's a good analogy. And field tests often contradict this assumption. They frequently show much higher stiffness values in reality, often between 300 MPa, sometimes even up to 600 MPa. This indicates that the CBGM layer often remains in its first strong, uncracked phase during construction and early life. It doesn't immediately crack like the catalog assumes. Interestingly, even the authors of the catalog themselves suggested it would be more rational to adopt stiffness values somewhere between the large and small block cracking states, rather than always jumping to the weakest small block cracking assumption.
So there's a disconnect between the standard assumption and what actually seems to happen in the field.
There certainly appears to be, and this has real economic and resource implications, potentially leading to unnecessary material costs, maybe longer construction times.
It's really fascinating how a seemingly small assumption buried in a design manual can have such a potentially big impact on a massive infrastructure project. The study also mentions a crucial practical step they take on site, placing an unbound aggregate layer on top of the fresh CBGM. What's the purpose of that? How does that fit in?
Yes. That aggregate layer plays a really important dual role. It's critical, actually. Firstly, it helps the CBGM cure properly. It limits moisture loss, which is essential for the cement hydration process, for it to gain strength effectively. But maybe more importantly, it acts as a protective shield, a cushion against the heavy construction traffic. This cover is vital because it protects the fresh, still relatively vulnerable CBGM from high vertical stresses. It helps prevent that premature cracking we talked about. It allows it to stay in that desirable, strong, uncracked state during the construction phase, which is when some of the heaviest loads might occur.
Okay, so it's a practical safeguard against the very cracking that some design models seem to assume will happen almost immediately.
Exactly. Without it, premature cracking, or even a kind of crushing fatigue, would be a real risk from those heavy 50-kilo and wheel loads mentioned in the study. It further complicates those stiffness assumptions.
Okay, now let's talk about predicting that fatigue life itself, because the study really highlights how challenging this is when Different models, different prediction methods can give you dramatically different answers. They paint completely different pictures of a road's future.
They really do. A comprehensive review back in 2018 by Pisjeska and Gajeski found a wide variety of these fatigue criteria exist. But for hydraulically bound layers like CBGM, two criteria really stand out in this study, and they represent quite different approaches. It's like they're using two different crystal balls to predict the road's future. First, there's the Dempsey criterion. This has been used in Poland, and it's known for yielding the lowest fatigue life values. It makes it very conservative, very cautious.
Lowest values, meaning it predicts failure sooner.
Yes, much sooner. It's based on a formula using the tensile strength and the calculated tensile stress at the bottom of the layer, essentially, how much the layer is being pulled apart versus how much pulling it can take. For the calculations, Dempsey proposed assuming the tensile strength is only 1/5 of the compressive strength. So in this study, with a compressive strength of 2.4 MPa, the flexural strength, the strength against bending and cracking, was set at a very low 0.48 MPa.
So that's one approach, conservative. What's the other one?
The other is the De Beer criterion, and this one provides significantly higher fatigue life estimates, much more optimistic, you could say. And crucially, this criterion was calibrated through extensive field testing using something called a heavy vehicle simulator, or HVS.
HVS, so real-world testing.
Exactly. This isn't just theory based on lab samples. It's based on how road sections actually perform under controlled, accelerated, heavy traffic loads in the field. That makes it potentially more reflective of real-world performance. It considers the tensile strain, how much the material stretches, and compares it to a specific failure strain limit, which was 125 microstrain in this case, a very small amount of stretch. It also includes a factor for shrinkage-induced cracking.
Okay, so we have Dempsey, very conservative, predicting early failure, and De Beer, field-calibrated, predicting much longer life. Two different models, two ways of looking at the same problem. How did the study actually apply these to a real-world type scenario?
Right. The researchers used BIZAR 3.0 software. It's a widely used tool for this kind of mechanistic pavement design. They used it to calculate the stresses and strains for a specific CBGM layer. It was a C1.52 layer, that common type, with a compressive strength of 2.4 MPa. And they simulated a standard wheel load of 50 kilonewton over it.
50 kilonewton, it's like a heavily loaded truck axle wheel.
Roughly, yes. It's a standard load used in these calculations. They then applied both Dempsey's and De Beer's criteria to 4 different pavement layer configurations. These varied in terms of layer thicknesses and the strength of the underlying ground, the subgrade.
And the results? You said earlier they were eye-opening. What did they find when they put these two fortune tellers, Dempsey and De Beer, to the test on these configurations?
They are really staggering. For 3 of the configurations, types 1, 2, and 3, the Dempsey criterion predicted, well, instantaneous failure.
Instantaneous, meaning zero life.
Pretty much. What it means is that the calculated tensile stresses right at the bottom of the CBGM layer immediately exceeded the assumed flexural strengths, that very conservative 0.48 MPa value. So essentially zero fatigue life in terms of progressive damage under that construction traffic load. According to Dempsey, the road would crack almost immediately under the first few heavy trucks for these designs.
Wow. Instantaneous failure. That sounds pretty dire. I imagine that's not a coal an engineer wants to get from the construction site on day one. Boss, the road cracked already.
It's certainly not ideal, and it's especially striking when you compare it directly to the De Beer criterion results for the exact same configurations. For those same types 1, 2, and 3, De Beer predicted fatigue lives ranging from 143,000 repetitions up to over 1 million load repetitions.
1 million compared to instantaneous failure.
Yes. And for the 4th configuration, type 4, which was a bit more robust, Dempsey predicted only 48 load repetitions, still practically immediate failure. But De Beer, for that same type 4, De Beer estimated an astonishing 2,858,260 repetitions.
2.8 million repetitions versus 48.
Correct. In that type 4 case, the calculated tensile stress was 0.40 MPa, which is below Dempsey's 0.48 MPa limit only just, leading to the 48 reps calculation. But the calculated tensile strain was 85.06 microstrain, well below De Beer's 125 microstrain limit, hence the millions of reps prediction.
That's a massive, almost unbelievable discrepancy. I mean, we're talking about a difference between a road failing literally as it's being built versus lasting for hundreds of thousands, even millions, of heavy truck passes under those same initial conditions. So what does this really mean for road designers, for budget planners, and ultimately for the durability and cost of the roads you drive on. This isn't just some academic debate in a journal, is it?
No, absolutely not. This has real-world consequences.
It feels like it means we might be spending more money than needed if we follow Dempsey, or maybe even building roads that don't last as long as they could if we trusted the more field-tested models like De Beer. What's the actual cost or benefit tied up in such a massive difference in prediction?
Well, this study really highlights, as the authors state, the conservative nature of Dempsey's method compared to the more field-calibrated De Beer approach. The dramatic difference really underscores the significant uncertainty that still exists in accurately characterizing the fatigue behavior of CBGM. It's complex stuff. It shows that relying on overly conservative assumptions, like Dempsey's, might lead to structures that are much more robust than predicted by that model, yes. But it could also mean unnecessary material costs. More cement means a higher carbon footprint, too, and potentially slower construction.
So we might be over-engineering based on potentially flawed prediction.
Or at least an extremely cautious one. Conversely, if the Dempsey model is truly too conservative, using it might mean we're missing opportunities to optimize designs, perhaps using slightly less material where appropriate, without actually sacrificing durability based on real-world performance patterns suggested by De Beer. It really raises the critical need for continued research. We need to develop and validate fatigue criteria that accurately reflect how these materials behave under realistic conditions. And critically, these need to be supported by real-world data, like that from heavy vehicle simulators. It also reinforces the importance of just good basic design. Proper structural configuration and adequate layer thickness are still key. Because while thinner or more heavily loaded configurations might seem efficient on paper, they can definitely lead to premature cracking if they're not properly verified with the right validated models.
So this deep dive into just one single study reveals some incredibly important lessons, doesn't it? Not just for engineers, but really for anyone who relies on our infrastructure and, pays for it through taxes.
Indeed. The study's conclusions are pretty stark when you lay them out. Based on the Dempsey criterion, only one of the 4 analyzed configurations, type 4, would even survive the initial construction traffic without immediate cracking. Just one. But according to the De Beer criterion, none of the structures were expected to fail under those same technological traffic loads. None of them. That difference is just profound. It paints 2 entirely different pictures of a road's resilience right at the start during construction. And furthermore, the research strongly indicates that the practice, at least in the Polish context they studied, of assuming stiffness modulus values for CBGM layers that are twice as low as for simple crushed aggregate. Well, it might be unjustified. Unjustified because field tests show it stays stronger for longer. Exactly. Using these overly conservative reduced stiffness values in the mechanistic calculations can result in an over-designed pavement structure. And this isn't just an engineering detail, it directly impacts public funds. It could mean unnecessary material costs, slower construction, maybe even an inefficient allocation of resources, all without necessarily providing a corresponding benefit in the actual lifespan of the road, especially given what field performance actually shows in the early life of these layers.
So we have to ask if we're building roads that are, in a sense, too strong in the wrong ways, or perhaps designed based on overly pessimistic assumptions.
That's certainly the question this research puts on the table. Are the models accurately reflecting reality, or are they leading to potentially inefficient designs?
So wrapping this up, what's the big takeaway here for the future of road building? Not just in Poland, presumably, but maybe around the world where similar materials are used.
I think the research strongly suggests that future efforts should really focus on defining fatigue criteria and material parameters that are specific to the regions where these road pavement structures are being designed and constructed. Using local materials, local conditions, and perhaps most importantly, calibrating models with local field performance data. One-size-fits-all criteria, especially highly conservative ones not backed by local field data, might not be the most efficient or accurate approach. It's really about striving for more precision, being more data-driven, and ultimately being more cost-effective and sustainable in how we build these vital arteries of our modern world.
What a fascinating journey into the unseen world beneath our feet. We've really unpacked how sophisticated engineering models try to predict the lifespan of our roads, and discovered just how much uncertainty can still exist when different criteria, different prediction methods are applied. That difference between instantaneous failure and millions of load repetitions, it's truly a wake-up call.
Yeah, and if we connect this to the bigger picture, it really is about optimizing our infrastructure investments for the long haul, isn't it? Understanding these material behaviors better, refining our predictive models using real-world data. It's absolutely crucial for building roads that are not only safe and durable, but also cost-effective and built with, let's say, precision engineering based on evidence.
It really raises an important question for you, listening right now. How much do you think we truly understand the long-term behavior of the materials we rely on every single day? And what kind of conservative, or maybe even outdated assumptions might be baked into other structures all around us that we just take for granted? Bridges, buildings, who knows? It's a powerful reminder, I think, that even the most fundamental parts of our built world are still subjects of ongoing scientific exploration, and there's always more to discover about making them better, smarter, and more efficient.